lately. My name is Dr. Mill, and I've been promised to share the session on theory. And the first talk in this session is entitled Turning Online Ciphers Off, and it's short work between Elena Andreeva, our general chair, Guy Barlow, Ritan Baumik, Igor Landi, Dan Page, and Martijn Stam, and Ritan will lead us.
So in this paper we studied online ciphers and offline ciphers and how to go between them. So I'll begin with introduction to what are online ciphers and offline ciphers. So I hope everyone is familiar with the idea of permutations here. It's just an invertible function where the domain and the codomain are the same. And we call a permutation online. So firstly, let's say we break things up into chunks, we call them blocks. So we assume that all blocks are elements, and we assume that all the underlying primitives, so these are generally built from some small fixed length primitives, and that is generally the size of the block. So as permutation is called online, if the ith block of the ciphertext depends only on the first I blocks of the message. So essentially it's being computed online. As the messages come, we can keep computing the ciphertext. On the other hand, offline permutations, wait for the entire message, then they'll start computing. So probably even C1 will have randomness of the entire message. But that does not happen in online. And so we can think of online ciphers as a kind of applicable block cipher where the tweak length is variable. So so it just takes one block input, mi, but it also takes a tweak, which is all the previous messages, and then it outputs here. But then if we think of it in this model, then we'll probably have to allow an empty tweak as well, or maybe we can consider the M1 to C1, that's just a regular block cipher, and erase this tweak a bit. So what essentially happens in an online cipher, when we say online cipher, is that it is online, but other than that it does not give any extra information. So in an online cipher, so if two message queries have a common prefix, then the ciphertext, corresponding ciphertext will also have a common prefix. So it shows these patterns of shared prefixes, but it does not show anything else. And more importantly, notice that the I plus 2th block is also the same in these two examples, but the I plus 2th block of the ciphertext varies because there has already been a change in the I plus 1th block. So once the prefix breaks, after that it's completely random. So what are the advantages of online encryption? The main advantage is that it's a single pass encryption. So you can compute the ciphertext on the fly, so it's fast, efficient, so it's lightweight. You don't have to you don't have to remember things. You can just throw off this plain text as they come. But the disadvantage is that since this information about the shared prefix is being leaked, so it cannot really be SPRP secure. So I can always make two queries with a same shared prefix, and then that will also give the same shared prefix in the ciphertext, which is very unlikely to happen in a true random permutation. So this is not SPRP. So SPRP, I think people are familiar. It's a strong pseudo-random permutation. It's a permutation which is secure in a chosen ciphertext attack scenario. And we'll use this term a few times here. SPRP and PRP. PRP is just a pseudo-random permutation. Right. And we also consider something which is almost online, but there's a subtle difference. It's called online but last. So here we only, as such a cipher only leaks information about shared proper prefixes. So last block is always random. Last block does not have that online property. So in a truly online cipher, if we query a message, query something, and then later query a prefix of it, a proper prefix, we can predict the entire ciphertext. But here we can never predict the entire ciphertext of a new query. There is at least one block of randomness. Okay. So now the problem we are trying to handle here. So let's say we have ideal online ciphers as primitives, and can we use them to build an offline cipher, build a proper cipher? And so what are the others? So ideally what we want is that this online cipher will be the only nonlinear component in our design, and the other layers will be just linear mixing layers. And we only consider some specific linear layers for the design, so though there are some results for the general linear layers as well. And these layers are very simple ones. It's a right block shift. So it's like a bit shift, but in the sense of blocks. So the last block comes at front, and the other blocks shift one is to the right. Left block shift, which is the other way around. And finally a blockwise reversal. These are three very straightforward linear mixing layers, and we only considered that. And now, what is the construction? So what is the construction we are aiming at? So this is the proposed construction that we keep. So the first one will be E of K1. So we generate R random keys for the ideal online cipher, and we take R layers of it, and we interleave them with linear mixing layers. So there are R-1 layers of L, L is the linear layer, and R layers of E. And all the layers are independent. Maybe that can be taken care of by masking or something better. So this is the generic design. So the parameters we can vary is R, the number of layers, and L, the linear mixing layer. So let's see what we get from that. So the first result is that if there is on any two-layer construction where there are two layers of ideal online cipher with one layer of mixing in between, for any L, there is a generic birthday attack. Because we don't know how L works, and we know that L is a linear layer. So y1 may or may not be a linear function of x5, which is x5 or xl. Here I have just taken 5 blocks. So the first block of y here, after the mix may or may not have linear dependence on the last block of x. But the thing is, if it does not have linear dependence, there is an even easier attack, because we can just make 2 queries, only differing in the last block, and then it will, after the first encryption, it will only differ in the final block, and then since the final block does not affect y1, in the after L, y1 remains same, and so after the final call to the online cipher, c1 remains same. So you can easily distinguish with 2 queries. So at least for anything, if we have to achieve anything, y1 must have some dependence on x5 or xl, the final block. And if there is some dependence, then we know that if we just again, if we keep everything same, vary the last block of the message, then after a point, in an ideal offline cipher, we should, if we make birthday many queries, we should get a collision in C1. But here we can never get a collision in C1 for the same reason. Because if y1 has a linear dependence on x5, it will keep changing each time. So after birthday many queries, we will still have all distinct C1, which will be a distinguishing attack. So this is a generic attack which works on any 2-layer construction. So we can never go beyond birthday. And so here's a summary of the security results for various 2-layer constructions. So first we notice that for left shift it's never secure, because left shift does not have that property. In left shift y1 is independent of x5, it does not depend. So if you just left shift and do another online encryption, and if you keep the first few blocks same, you will always get the same first ciphertext block. So it's never secure. But you can see the right shift. So for the right shift, the problem is the inverse is a left shift, a 2-layer with a left shift. So the inverse cannot be secure. So if you allow the adversary to make chosen ciphertext attack, it will break. Okay. So this can at most be a birthday secure PRP, which does not allow inverse queries. And this in fact can be proved. So it's proved in the paper that it is a birthday secure PRP. And it's more interesting for the 2-layer with reverse, because there's a lot of mixing. So we can expect that it will be probably secure, but the thing is there is a CCI attack, which is a ciphertext attack, which I'll show on the next slide. But this can be shown to be a partly secure SPRP if we use an online but last cipher, where there's randomness in the last block. But if there's not, we can exploit that to make an attack. Okay, so let's look at the attack. Yeah. So the attack is quite simple. We can make up first the 3-block queries. We get some x1, x2, x3, which are the internal values, and then 3 ciphertext blocks. I've just numbered them in the reverse order because that makes it easy. So C3, C2, C1, and then we inverse query with C3, C2. We get the same x3, x2 because that's the prefix, and then when it changes to x2, x3, then we don't know anything about the plain text. So we get 2 new plain texts perhaps, P2 prime and P3 prime. And then we query again with the, that will be P1, P2, P3 or M1, P2. So that's M1 and M2 in the third query. So in the third query, we again query with M1 and M2. We know that the first layer will be X1 and X2 because that's the prefix. And then after X1 and X2, it reverses, becomes X2, X1. We don't know anything about C2 prime and C1 prime. What we know about C2 prime is that it's the encryption of X2 in the lower online cipher. And from the second query, we know that X2 is the encryption of P2 prime in the first online cipher. So if we combine these two, if we query P2 prime, we know that we can predict the ciphertext. It will be C2 prime. But of course, if it's online but last, we are using that a lot. We have the knowledge that a proper prefix, for the proper prefix, the entire ciphertext is revealed. We are actually using that, but this attack cannot work in an online but last cipher. So that's mostly it with the 2-layer constructions. And as for the 3-layer constructions, they do better. But the 3-layer with left shift is still insecure. It just shifts twice. We have 2 layers, but still the first few blocks will not be affected. If we keep a long enough prefix, actually left shift never will work if we have a long enough prefix message. It can only work for small messages, maybe, if we have enough layers. And so the same problem remains for the right shift, that it can be attacked in the CCL, but it turns out to be an in-bit secure, like optimally secure PRP. So when you do not allow chosen ciphertext attacks, this 3-layer with right shift achieves beyond birthday, in fact, almost full n-bit security, where n is the size of the probable underlying primitive, or it's the block size. And so what about the 3-layer with reverse? So 3-layer with reverse is an n-bit secure SPRP. It can be shown, but the thing is we have to make a restriction. It has to be in the AIL setting, or the arbitrary input length setting, where the messages have some arbitrary length, but it's fixed. It's not variable. So in the variable sense, the proof becomes difficult. We could not edit, so it's open. But if we replace it by online but last ciphers, it's probably easy to prove, but we didn't explore that. That's not very interesting. We were more interested in what we can do with the purely online ciphers. And yeah, so there's a natural question that, okay, so since adding one layer improves things, so do we keep adding layers? Do we get security beyond n bits? Yeah. So that does not happen. So there's another result at the end of the paper which shows that after a point, if we add more layers, in fact after 3, so it can only change the constant factor, but it will not give you higher and higher security. So probably the 3-layer with reverse is the most optimal construction we got out of this. But there's another open problem. We believe that maybe, so right shifting with a few layers will never give SPRP security because of that attack. But maybe after enough layers, does it happen? Does things get mixed up enough? But that's another open question. Yeah, so that's mostly it. Okay, thank you for
Any questions? So just for clarification, you have this general result that says more layers doesn't help. Is this identical layers, or they can all be different as well?
No, we have only explored identical layers.
So the answer could be different for different layers?
For different layers, it could be. It has not been explored, but I think my guess is that probably not.
Okay? There's no more questions. Let's thank the speaker again. Thank you very much.